Hi, in this video, we are going to look at some more problems for RMO and IOQM exams. The first problem is a proof question. It says in a set of integers which contain both positive and negative elements, the sum of any two elements, not necessarily distinct, is also in the set, Now what we have to prove? We have to prove that the difference of any two elements, also lies in the set. Okay. So we have a set of integers which have both positive and negative terms. The sum of any two elements in the set will also be in the set, right? So we have to prove that the difference will also be in the set. Okay. So first of all, we'll do a simple induction to prove that if C, which is an integer, belongs to the set, then n times C will also belong to the set. Here n is an integer. How do we do this? We can do a simple induction. Base case is assume C is in the set. So if n is equal to 1, it automatically implies nc, which is 1 times C is equal to C belongs to S. Now, for the induction step, assume nc belongs to the set. Then if you think about n plus 1c, that is equal to nc plus c. And we already know that nc belongs to the set and c belongs to the set. And by the property, the sum of any two elements belongs to the set. Therefore, this n plus 1c is belonging to S. So that finishes off the induction. And therefore, we know now that if C belongs to the set, where C is an integer, any multiple of C also lies in the set, right? Once we have this induction done, now what we will do is go towards solving the problem. Here we will assume, not assume, actually we know that since the set consists of integers, is a set of integers, there will be a minimal positive integer A belonging to S and a maximum negative integer or greatest negative integer B, which belongs to the set S. Basically, what am I saying? If it's a set of integers, there will be a minimum positive integer and a maximum negative integer. We are calling them A and B. So A belongs to S, B belongs to S. A is positive, B is negative, and A is the least positive integer. And B is the maximum negative integer that belongs to the set. Right? Now, because of this, we can say that because of the property of the set, A plus B also belongs to the set, right? Because two elements are A and B, and so the sum of the elements will belong to the set. And because A is positive and B is negative, we can say B is less than A plus B is less than A. And now we can prove a very nice thing where we say that if A plus B is greater than 0, then A plus B is less than A, and A plus B is the least positive integer now. least positive integer belonging to the set. But that is not possible. That is a contradiction because we have assumed that the minimum positive integer is a. So this is not possible. Similarly, if a plus b is less than 0, then a plus b is the greatest negative integer. Greatest negative integer belonging to the set. Because a plus b is bigger than b now, and b was supposed to be the greatest negative integer belonging to the set. So this is also not possible. So what this means is the only possibility is a plus b is 0, which implies b is equal to minus a. So what we know now is that whatever is the minimum positive integer, the maximum negative integer is negative of a. So we know that a belongs to the set and minus a belongs to the set. And obviously then 0 will also belong to the set. And from the previous induction, we know that all the multiples of a will belong to the set. So we know a, 2a, 3a, 0, minus a, minus 2a. All of these are elements of the set, right? What we will prove now is there is no element in the set. There is no element in the set which is not an integer multiple of a. Not an integer multiple of a. So far what have we done? We have proved that the set has elements like this. Minus a, minus 2a. But we have not said anything about other types of integers in this set, right? So now what we are saying is there is no element in the set which is not an integer multiple of a. We'll prove that by contradiction. Assume, suppose there is a non-multiple of a in the set. Non-multiple of a in the set. So any such number which is not a multiple of a can be written as q times a plus r by the division algorithm. Here r is less than a. Because this number, let's call it c for the time being, this number c is not a multiple of a, we can use the division algorithm to write it like this. Here q is an integer, right? Great. So let's say this number belongs to the set. qa plus r belongs to s, right? Obviously, we know that any multiple of a also belongs to the set. We already have proved it. So there will be a minus qa belonging to s also. And if these two belong to the set, then the sum of them, when you add them, you get r, and r should belong to the set. But r is a number which is positive and less than a, which basically means r is the least positive integer in the set, which basically contradicts what we have said earlier that a is the least positive integer in the set. So therefore, that means that this assumption is incorrect. This is a contradiction. R cannot be the least element which is positive in the set. So that means that there is no element in the set which is not an integer multiple of a. So basically the set now consists of what? The set is S is basically n times a, where n belongs to integers. All integer multiples of a belong to the set, and n can be positive or negative integers. And obviously no other integer elements are there in the set, right? Now this set has been established. What we wanted to prove was that the difference of any two elements is also in the set. Which is very easy now. If there are two separate elements, let's say n1a and n2a, the difference of these two is what? n1 minus n2 times a, which is also a multiple of a. So therefore, by definition of the set, any multiple of a belongs to the set. So therefore, n1 minus n2 times a belongs to the set. We already know this. So we have proved our statement. So an interesting problem which uses our understanding of the set and establishes what the set actually looks like. Let's move on to the next problem. This is question 93. Let n be a positive integer. Let n be a positive integer. Prove that if 2 plus 2 times root over 28 n square plus 1 is an integer, then it is the square of an integer. Then it is the square of an integer. Okay, so let's think about it. We will say let m be equal to 1 plus square root of 28 n square plus 1. And we will simplify this equation a little bit. M square is equal to, or actually I will simplify it like this. I will take m minus 1 on this side and then square it. M minus 1 whole square is equal to 28 n square plus 1, which means m square minus 2m plus 1 is equal to 28 n square plus 1, which means m square minus 2m is equal to 28 n square. Right. So what this means is, this implies that m square lets me think about the parity of m. I want to think about whether m is even or odd. So if n is even, then obviously okay, let me think. Is it possible for m to be odd? If m is odd, then m square is odd and 2m is even, and the difference of m square minus 2m is odd. But the right hand side RHS, which is 28 n square, is even. So this is impossible. So this is impossible. So that means that m is even. So if m is even, m can be written as 2k, and we put that 2k here, we get 4k square minus 4k is equal to 28 n square, which means we have k square minus k is equal to 7n square. So k into k minus 1 is equal to 7n square. And since k and k minus 1 are relatively prime to each other, relatively prime, therefore they don't have any common factors. Therefore, one of them is a square. One of them is a square. And the other one is 7 times a square. Other one is 7 times a square. Right? Why am I saying that? It cannot be that k and k minus 1 cannot be of the form 7. Can it be 7n into n? No, it cannot be, because then they will have a common factor, right? So what we can say is it has to be of the form n square and 7. K must be n square and k minus 1 might be 7. Something like that has to happen. So, or k minus 1 is n square and k is 7, right? Both of them cannot have a common factor. So they cannot be of the form 7n and n, because k and k minus 1 are co-prime, right? So what we will do here is suppose k minus 1 is equal to some h square for some positive integer h, positive integer h. In that case, then k is divisible by 7 because k must be 7 in that case. So k is divisible by 7 and therefore h square is congruent to 6 mod 7 because k minus 1 is h square. K minus 1 is basically 6 mod 7. So h square is congruent to 6 mod 7 is coming. However, a square can only have these residues, can only be congruent to 0, 1, 2, and 4 mod 7. This is a property of squares. If you don't understand this, you have to go to the quadratic residues section in my course on number theory. The course is available on Udemy. I have discussed quadratic residues in detail. You need to study that a little bit. A square can only be congruent to 0, 1, 2, and 4 mod 7, which means that this is impossible. H square cannot be congruent to 6 mod 7. So if k minus 1 cannot be h square, then the other option is k must be h square instead, right? And if k is h square, then 2 plus 2 times root over 28 n square plus 1 is equal to 2m, which is equal to 4k, which is equal to 2h whole square. Basically, it's a perfect square in this case. Because if k is h square, then m is what? M is 2h squared, right? And if m is 2h squared, you have to revisit the argument in the previous screen here. This m was what? M was 1 plus 1 times root over 28 n square plus 1. So 2 plus 2 times this is basically 2m, right? We had started off with m being 1 time this, right? So this is 2m and m was 2k. So this is 4k and k is h square. This is becoming 2h whole square, 4h square, which 2h is an integer. So we have proved that this is a perfect square. This is what we wanted to prove, but we started off with 1 plus 1 times this. We called that as m. And that's how this whole proof works. We called this one as m and we worked through the whole thing and we got m is even and then we found out what k can be. K has to be the square of an integer h. And that's how this proof is done. Hopefully you have followed the proof. If you haven't, go back to the previous screen and work through the steps. You will realize that it works. Okay, let's look at the next problem. Question 94. Let the lengths of the sides of a triangle be A, B, and C, and the measures of the opposite angles and the measures of the opposite angles be alpha, beta, and gamma, respectively. We have to prove that the triangle is equilateral if A times 1 minus 2 cos alpha plus B times 1 minus 2 cos beta plus C times 1 minus 2 cos gamma is equal to 0. Right. So, right. So this problem, we have to prove that the triangle is equilateral if this condition is true, right? So we can apply sine rule and we can say A by sine alpha is equal to B by sine beta is equal to C by sine gamma is equal to 2 capital R. And from there we know that A is 2R sine alpha and B is 2R sine beta and C is 2R sine gamma. Now, if I put that in this condition, the condition changes to sine alpha 1 minus 2 cos alpha plus sine beta 1 minus 2 cos beta plus sine gamma 1 minus 2 cos gamma is equal to 0. I have cancelled the 2r factor. And this can be simplified like this. Sine alpha plus sine beta plus sine gamma is equal to sine 2 alpha plus sine 2 beta plus sine 2 gamma. I have used the double angle formula here. Now, there is a simple trigonometric identity. If alpha plus beta plus gamma is equal to 180 degree, you can prove that sine alpha plus sine beta plus sine gamma is equal to 4 cos alpha by 2, cos beta by 2, and cos gamma by 2. This is an identity that is there in SL Loni, and it's a simple enough proof. You can do this yourself. And also you can show that sine 2 alpha plus sine 2 beta plus sine 2 gamma is equal to 4 sine alpha, sine beta, sine gamma. So our relationship was saying that sine alpha plus sine beta plus sine gamma is equal to sine 2 alpha plus sine 2 beta plus sine 2 gamma, which means now using these identities, I get 4 cos alpha by 2 cos beta by 2 cos gamma by 2 is equal to 4 sine alpha, sine beta, sine gamma. Let's see what that means. We can use the double angle formula on this side and say 4 times 8 sine alpha by 2 cos alpha by 2 sine beta by 2 cos beta by 2 sine gamma by 2 cos gamma by 2 is equal to, this side is 4 cos alpha by 2 cos beta by 2 cos gamma by 2. All of these terms can get cancelled. 4 gets cancelled. All the cos terms get cancelled from here. And what we have from this is that sine alpha by 2, sine beta by 2, and sine gamma by 2 is equal to 1 by 8. That is what our condition is boiling down to after some simplification. Right? We need to prove that this means it's an equilateral triangle. We have simplified it so far. We need to show that this implies that it's an equilateral triangle. So let's think about how we do that. So we have 1 by 8 is equal to sine alpha by 2, sine beta by 2, sine gamma by 2. And we will work with this right hand side here. So this side is actually can be written as half of cos of alpha minus beta by 2 minus cos of alpha plus beta by 2 times sine of gamma by 2. What have I done in this step? I have used the product to sum formulas, and 2 sine A sine B is cos A minus B by 2 minus cos A plus B by 2. I'm using that formula to write it like this. Okay. Now think of this. This is half times cos of alpha minus beta by 2, and alpha plus beta by 2 is 90 minus lambda by 2. So therefore, this is minus sine lambda by 2 multiplied by sine lambda by 2, right? So what we get here is an equation like this. And if you simplify this equation a little bit, it looks like this: minus half sine square lambda by 2 plus half cos alpha minus beta by 2 into sine lambda by 2 is equal to 1 by 8. So if you rewrite this equation a little bit, it will look like this: half times sine square lambda by 2 minus half cos alpha minus beta by 2 times sine lambda by 2 plus 1 by 8 is equal to 0. This is my equation that we are getting, right? Now it is obvious from this equation that if I write a quadratic equation like this, okay, first we'll multiply by 2 on both sides here. So we'll remove this half here, and make it 1 by 4, right? So the equation that I'm talking about is x squared minus cos of alpha minus beta by 2 into x plus 1 by 4 equals 0. And it is obvious that in this quadratic, sine lambda by 2 is a root. What am I saying? If I put x is equal to sine lambda by 2, this satisfies this equation, because actually that is the equation: sine square lambda by 2 minus this plus 1 by 4. So sine lambda by 2 is a root of this equation. And let's look at the discriminant of this equation. The discriminant of this equation is cos square alpha minus beta by 2 minus 4 into 1 by 4, so minus 1. And this discriminant is clearly less than equal to 0, right? Why is this discriminant less than equal to 0? Because cos square can never be greater than 1. And cos squared minus 1 will be something less than equal to 0. And since we have a real root, here, sine lambda by 2 is real. That means the discriminant cannot be less than 0. So that means the discriminant must be equal to 0. So we have this condition guaranteed, right? Which means that alpha must be equal to beta, right? And if alpha is equal to beta and cos of alpha minus beta by 2 is 1, from here, think about it. If alpha is equal to beta, we have cos of alpha minus beta by 2 is equal to cos 0 is equal to 1. So half of cos of alpha minus beta by 2 is equal to half, right? Correct. So the product of the roots, sine lambda by 2 is a root. Okay, actually I am done here. Because the discriminant is 0, the roots are supposed to be equal. So sine lambda by 2 is a root, then it's also another root. It's a double root. So we know that sine square lambda by 2 is the product of the roots, which is equal to 1 by 4 here, which means that sine lambda by 2 is basically half, which means lambda by 2 is 30 degrees, which means lambda is 60 degrees. And if lambda is 60 degrees and alpha is equal to beta, that means alpha is equal to beta is equal to lambda is equal to 60. All the angles are equal and the triangle is equilateral. So think about what we did here. We looked at the initial identity. We used sine rule to simplify it a little bit. We got the condition sine alpha plus sine beta plus sine gamma is sine 2 alpha plus sine 2 beta plus sine 2 gamma. We used conditional identities on a triangle to simplify both sides, and from there we got this result. Once we got this result, we are using product and sum product to sum formulas to simplify it a little bit and got it as a quadratic with root sine lambda by 2. Once you do that, you can prove that the quadratic has equal roots. And if it is equal roots, you can show now by product of the roots and sum of the roots. Actually, by the discriminant being 0, we know alpha is equal to beta. And once you know that, you can use product of the roots to get that sine lambda by 2 must be half. And after that, it's over. The triangle is equilateral. Okay, let's look at the next problem. This is question 95. And this is a probability question. Determine the probability that 5 numbers chosen at random from the first 90 positive integers contain two consecutive numbers. Right. We have to find the probability that that 5 numbers chosen at random from the first 90 positive integers. So you have to choose integers from 1 to 90. From there, if you select any 5 integers, we have to find the probability that they contain two consecutive numbers. So we start off by saying the total number of ways of choosing 5 numbers from 90. From 90 is obviously 90C5. Now, this is the total number of ways of choosing the 5 number. This will come in the denominator. Suppose no two of the 5 numbers are consecutive. So basically what we are saying is 1 is less than A. Let the 5 numbers be A, B, C, D, E. We have A less than B less than C less than D less than E less than equal to 90. This is the condition. The 5 numbers chosen are not consecutive, right? Therefore, there is a strict inequality between these 5 numbers. And A minimum number can be 1 and the maximum number could be 90. What we will define is define new variables P, Q, R, S. So we will say P is B minus 1, Q is C minus 2, R is D minus 3, S is E minus 4. Why are we defining these 4 integers? Because if we choose integers like this, we know that A, 1 is less than A is still valid, less than equal to A. But now we can say it's less than equal to P. A is less than equal to P, right? P is B minus 1. So, right. And then this is less than equal to Q. This is less than equal to R. This is less than equal to S. And S will be less than equal to 86. Why? Because S is E minus 4. So E could be up to 90. And now we are doing E minus 4. So S must be up to 86, right? And these set of inequalities are valid now. Here P, Q, R, S are 4 other integers such that they are equal to B minus 1, C minus 2, D minus 3, and E minus 4. So these inequalities are valid, and now we can choose the number of ways in which we can select these 5 integers A, P, Q, R, S, but now we have to select them from 1 to 86, right? So the number of ways of selecting these 5 integers, which makes sure that they original integers a, b, c, d, e will not be consecutive because there is a gap between them. P, Q, R, S are all, they can be equal to each other, but even if they are equal to each other, B and C and D and E will not be equal to each other. So the number of ways of selecting these 5 integers, A, P, Q, R, S, is basically 86C5. So the number of ways of selecting no such integers such that no two of them are consecutive is basically the probability of that is 86C5 by 90C5. 86C5 by 90C5. That is the probability of selecting integers such that no two of them are consecutive. So if we subtract that from the total probability, we get the probability that they contain at least two consecutive in numbers, right? We are subtracting the probability that no two numbers are consecutive from the total probability. And that will mean that at least some of them will be consecutive in the desired case that we get. So if you calculate this out, that will be your answer. It comes out to be 106081 divided by 511038. That is the probability. We are doing it by a complementary counting method. So we converted the problem from selecting a situation where we have to directly count two consecutive numbers. Instead of that, we did a complementary counting. We did no two of the numbers are consecutive. And how did we do that? We took, instead of selecting A, B, C, D, E, we took A, P, Q, R, S, where P and Q and R and S could be equal to each other. However, P is B minus 1, Q is C minus 2, and so on. So therefore, the upper limit for S becomes less than 90. And now it ensures that A, B, C, D, E will not be consecutive, right? So think about it. This is the way to do it. We have converted the counting problem and did a complementary counting here. Let's look at the next problem. Okay. Prove that A times B minus C whole square plus B times C minus A whole square plus C times A minus B whole square plus 4ABC is greater than AQ plus BQ plus CQ, where A, B, C are the sides of a triangle. Sides of a triangle. So usually in these types of problems, almost every time you have to use the triangle inequality. So let's think about how we will prove this. We have A times B minus C whole square plus B times C minus A whole square plus C times A minus B whole square plus 4ABC minus A cube minus B cube minus C cube. We will work with this expression, and ultimately I want to show that this expression is greater than 0, which will mean that the inequality is true. So let's think about how we do this. We will group the terms together. I will take this term, and I'll take A common. I'll get B minus C whole square minus A square. And similarly, I'll take B common here and with B cube. So I'll get C minus A whole square minus B square. And C common here, and I'll get A minus B whole square minus C square plus 4ABC. Right. Okay. Then this means right. This means that this is becoming A times B minus C plus A multiplied by B minus C minus A plus this becomes B times C minus A minus B and C minus A plus B and C times A minus B minus C and A minus B plus C plus 4ABC. Right. Let's think about these terms here. A plus B minus C is a term here. A times you have A plus B minus C here, B minus C minus A, and I can write this as a negative B, A plus B minus C, C minus A plus B. And this is C times A minus B minus C, A minus B plus C, plus 4ABC. Right. Let's take A plus B minus C common from the first two terms. If I do that, I get A plus B minus C common here. And I get A times B minus C minus A minus B times C minus A plus B. Okay. And I have these two terms still left over, in which I can take C common, I think. So I will work with that here itself. Let me just rub off this. So simplifying this, A plus B minus C common, we have here AB minus C AC minus A square. Okay, I'll just write it out. AB minus AC minus A square minus BC plus AB minus B square. And plus C common, I have A minus B minus C, A minus B plus C plus 4AB, right? So this becomes 2AB minus A square minus B square, 2AB minus A square minus B square minus C times A plus B. This term, this term, this term, and this term has been taken into account. And you have A plus B minus C here. And here, what do I get? Here I get A minus B whole square. And A minus B minus C, A minus B plus C, minus C square. Plus 4AB. This becomes A plus B whole square minus C square. Right. So this term, the second term here is becoming C times A plus B plus C and A plus B minus C. And here you have A plus B minus C. And this term is minus of A minus B whole square minus C into A plus B. Right? This is minus of A minus B whole square minus C into A plus B. And between the first term and the second term, I can take A plus B minus C common. So I will do that now. If I take A plus B minus C common between the first and second term, I get a minus of A minus B whole square minus C into A plus B. plus C into A plus B plus C. Nice. I'm taking here this term and this term. I'm taking A plus B minus C common. And notice here that plus C into A plus B will cancel this term completely. And you will be left with C square minus A minus B whole square here. So if you think about it now, it is becoming A plus B minus C times C minus A plus B times C plus A minus B. So after all of these steps, the original inequality is transformed into this. And this is clearly each term is positive by triangle inequality. ABC are sides of a triangle. So A plus B is greater than C, C plus B is greater than A, and C plus A is greater than B. So this is greater than 0. And that is what we wanted to prove because we had converted the inequality that we needed to prove into a expression with on the LHS. We wanted to show that this LHS expression is positive. And that's what we have gotten here. So that concludes this problem. Go through the steps carefully. If you're not getting it, you'll realize that it is all working out, right? Okay, so that finishes our session for today. We will go through the next 4 or 5 problems in the next class. I'll see you next time.